starting with this webinar, let me define you the flood. So what is flood? Right, it is a natural disaster which results into loss of life, property, etc. when excess amount of water enters into the rivers or streams and overtops the banks of the river. Right, so that is the basic definition of a flood, that when excess amount of water enters into the river and it overtops both the banks of river, it will cause loss of life, property, etc. in the nearby floodplain area. And there are many ways in which we can control or prevent flood. But as I have always said that flood is a natural disaster, right? We cannot stop it permanently. So we can only control or prevent it by forecasting it. So once we can know that if this much amount of flood or this much magnitude of flood is going to happen, then we can take relevant preventive or control measures. One of the example of prevention of flood is like we can manage the floodplain area well, right? If we can get the information on time that this much amount of water is going to come in the river, then we can manage the people to evacuate in the nearby areas. Second method is we can construct flood walls. Gujarati there is a famous quote that "Poor aave tyare paad bandhe." If you have heard that quote, right? So what does it mean? It means that we need to construct the flood walls before it comes, so that the water remains in the river itself and it will not overtop on the sides of the river. Right, then the other way is to divert your flood into a small pond, so that for temporarily purpose the flood can be we can avoid it. So there are many such ways in which floods can be controlled, and one such method today we are going to study using this software. So now let us understand the meaning of your topic: one-dimensional hydrodynamic flood modeling. What do you mean by modeling? Right, so modeling is a process in which any physical or real existing phenomenon is expressed by a set of mathematical equations using computers, where programming is done. So what does it mean? That it means that any real on-field condition, we can describe it with the help of computers, that is using a software. So here we are going to model what? Here we are going to model a flood, right? We are going to describe an on-field real condition of flood using a software HEC-RAS, where the flood is one-dimensional as well as hydrodynamic. Okay, so let's begin with the webinar. So HEC-RAS software was developed at the Hydrologic Engineering Center, which is a division of the Institute for Water Resources, IWR, US Army Corps of Engineers. HEC-RAS is designed to perform one-dimensional as well as two-dimensional hydraulic calculations for a full network of natural and constructed channels. See, natural channels refers to the rivers, streams, etc., while the constructed channels refers to the irrigation canals. Okay, so it can perform hydraulic calculations, or it can perform modeling for both one-dimensional and two-dimensional networks of natural and constructed channels, then overbank or floodplain, right? So overbank or floodplain is the area which is lying on both the sides of your river. Then levees, protected areas. Again, the flood walls are also referred to as levees. So the areas which are protected with these levees, they can also be simulated with the help of this software. Now, dear students, see, these are the different components in which this HEC-RAS entire modeling system is divided. Right, you can see here 5 components are given. First component is 1D steady flow hydraulics. Into bracket, it has been written water surface profile. So first of all, you must know the meaning of steady flow as well as one-dimensional flow. So steady flow, it is a type of flow in which the properties of fluid are not changing with respect to time at any cross section. right? For example, if I say that if the velocity of flow at a particular time in a river is 2 meter per second, then after some time the velocity will be same, that is 2 meter per second. So that is referred to as a steady flow. And one dimensional steady flow means the river water is flowing only in one direction, it is not flowing in any other direction. So when the flood water is flowing in the river itself, it is not getting spread on both the sides of river, then it is known as one dimensional flow. And along with the water flowing in the river, if it is getting spread over both the banks of the river and enters into the nearby city or area, then it will be considered as a 2D flow. So students, be very clear with this, that one dimensional flow is a type of flow in which the flood is moving only into the river, or we are concerned only with the water, which is flood water, which is flowing in the river or a stream. And the flow is which kind of flow? Steady flow, right? So second component, you can see that it includes both 1D unsteady flow simulations as well as 2D unsteady flow simulations. So as you are carrying out 1D steady flow hydraulics, you can also calculate 1D unsteady flow hydraulics and 2D unsteady flow hydraulics. Then the next component is you can also carry out combined flow analysis of 1D and 2D flow. The next one is you can also carry out the simulation process of sediment transport, that is the movable boundary channel. And the last one is water quality analysis. This modeling system is very large and it includes very interesting features, but because of time limitations, we are going to study only the first component, that is 1D steady flow hydraulics. Okay, so now let me explain you with an example that what exactly we are going to study today. Now, if I take an example of flood which took in a Tapi river during 2006 August, a huge devastating flood was occurred around the Surat city, which was lying on both the sides of the both the banks of the river Tapi, and the downstream portion of the river Tapi is lying nearby the Surat city, where finally it is meeting the Arabian Sea. Okay, so at that point of time, a huge loss of life, property, etc. has been occurred due to this flood. So what if we know that and at that time the discharge of water, that is the flood magnitude, was around 8.9 lakh cubic in Tapi river, which was released from Ukai Dam, right? So if we could know that this much amount of discharge is going to come into the river before the flood occurs, okay, so we could have managed the nearby areas lying that is the Surat city very well. But it was not modeled properly at that time, and because of some miscommunications from the Ukai Dam, this devastating flood was occurred. Now, the second way where we can prevent this flood is by construction of flood walls, that is levees. As I said, right, ke poor aave tyare pad bandhe. So what do you mean that pad? It simply refers to the walls which are constructed on both the banks of the river, so that the water will remain in the river itself and it will not overtop the banks of the river. So to construct these embankments or flood walls, we need to know that up to what elevation or up to what height these walls are required to be constructed, right? And to determine the height of the flood walls, it is required to determine the depth of water in the river at different cross sections. Okay, are you getting it? આપણે વોટરની ડેપ્થ રિવરની અંદર કેટલી છે એ દરેક ક્રોસ સેક્શન પર થોડા ડિસ્ટન્સ પર વી શુડ નો, સો ધેટ એના એકોર્ડિંગલી આપણે વોલ્સનો હાઇટ પ્રોવાઈડ કરી શકીએ. Okay, so that depth of water is also known as water surface profiles or water surface elevation, and that we are going to compute today using one example. Right. So I hope 20 to 30% of this has been understood by you, but I'll make you sure that at the end of this webinar, you will be clear with the first component of the HEC-RAS modeling system. Okay, so now let's begin with the working in the software. See, I have prepared a PPT, so don't get panic. Don't perform it. Just sit back, relax, and watch it. I will share the PPT with you, and this software is freely available, so you can download it from the Google and can perform on your own. Okay, so our today's output will be our today's topic is a steady flow one dimensional hydrodynamic flood modeling. Again, I am telling that we are going to model a flood, means we are going to represent a physical existing condition of flood on a computer or a software, on a software, and the flood is steady as well as one dimensional. Okay, so here flood modeling can be done by computing water surface profiles for a one dimensional gradually varied steady flow. Flood modeling કેવી રીતે થઈ શકે? It can be done by computing what we are going to compute, what we are going to get it as a final result, water surface profiles. Right, water surface profiles means depth of water at different cross sections. Which kind of which kind of flood? For a one dimensional gradually varied steady flow or a flood. So these are the 5 basic steps which we need to perform for the results. So the modeling process can be divided into following steps. First one is open the HEC-RAS software and create the file. Okay, so let's start with the software. See, right now this kind of window will get open. Step 1, opening the HEC-RAS software and creating a file. So here you can see this is the main window of your software. Here at the right hand side of the upstream of the main window, it has been written HEC-RAS 507. Dear students, this is the latest version which I have downloaded and I am showing you the calculations in it. So I hope the software is open. Okay. Okay. So here the main window of the software is open up. Right here you can see different options like file, edit, run, view, options, GIS tools, help. So what we will do, we will go to file, we will go to new project. Right, but first of all we need to define a drive in which we want to save our project. So I'll select a drive H. Now in that I need to create a new folder, so I am creating a new folder. Create new folder. Here it has been written that enter the name for the new dictionary on the drive. So I am going to give a name called flood modeling. Okay, so I'll click on OK over here. See, a folder has been created. Now in this folder, you need to save a file in which you are going to work. So you need to give a title. And what we are going to do, we are going to perform modeling of the first component of HEC-RAS model, which is steady flow one dimensional. Okay, so I am giving the title as steady flow one dimensional, and here you can see that the file name with an extension .prg, which is a default extension, has been shown over here. Right, so what I did, I go to the file, select a new project, I selected a drive. clicking on create folder, I made a folder, and in that folder I gave a name of the file in which I am going to work, that is steady flow 1D, with the title and with the file name steady flow 1D dot extension prg. Okay, now I am going to click on OK. So here they are showing something. What they are showing, they are saying that start a new project with steadyflow1d.prg as its file name and steadyflow1d as its title. Okay, so that is fine in the dictionary of flood modeling. Now, second point is written that the unit system will be set to US customary units but can be changed under the option menus on the main RAS window. Okay, so here we need to work on the metric system, that is the SI system of units. And before proceeding further, for the next step, we need to change it to the metric system units. So once I'll click on OK over here, so you can see here a name has came, project, where it has written steady flow 1D, and it has been stored in a folder of flood modeling with the file name steadyflow1d.prg. So this, if this appears on your main window screen, it means that your file has been saved properly. Okay, so let's change the unit here. Now I am going to click over here. See on the right hand side of the window at the bottom, it is written US customary units. So I will I need to change this to the metric system of units. Okay, so for this process, what I will do, I will go to the options. Here, options, right? You can see the third point, it is written as unit system, that is unit customary. So I'll go to options, unit system, that is unit custom, US customary. I will click over here. A box is opened up where it is written US customary. Since it has been developed by the US Army Corps of Engineers, their default system of unit they have set, but we are working in India and we want to work in our international system of units that we carry for almost all the processes, that is metric system of units. So I will choose over here. Here it is written that set as default for new projects. So no, I don't want to set this metric system as a default for all the projects. I want to set it for the current project only. Okay, so I click on the system international, that is metric system. I will click on OK button. Okay, so they are saying that you want to convert it into SI system. Yes, we want to convert it into SI system. And now students, you can see over here, right hand side at the bottom of the window, it has been changed to SI units. Okay, so what I did, I went to the option unit system, system international, and okay. So our project file is now saved into SI unit of system. So before starting with the actual work in the project, it is very necessary to change into the SI system of units. Okay, let me show you this in PPT. Okay, so what we did, we opened the HEC-RAS main window as shown in figure 1. Then we went to file, selected a new project, select the drive to save the file, create folder option, name of the folder. Here it is written flood mapping, we have given flood modeling, and give the title of the project as steady flow 1D. File name will be automatically set to this. Okay, so title will be this, file will be, name will be same but with an extension of .prj, and then press OK button. Hence, a new project file with project title name steadyflow1d will be created in the folder which is created in a particular drive. The name of the project will also be displayed on the main window. Now, see, read this point. Under the option menu on the main window, select option unit system and set the current project under SI system of unit. Okay, clear? So here we are done with our first step. That is, open the HEC-RAS software and create the file. Okay, so we are done with the first process. First step of the entire modeling system of a 1D steady flow hydrodynamic flood. Now what we are going to do next? We are going to enter the geometric data, that is the cross-sectional data of river reach under consideration. Under consideration means the study area which we have selected. Okay, so let's start with the second step. Okay, so now what I am going to do? See, I am going to click on the edit option on the main HEC-RAS window. Here you can see many options such as geometric data, steady flow data, quasi unsteady flow data, that is sediment analysis, unsteady flow data, sediment and water quality data. So we need to enter this geometric data. Okay, so such a screen is appearing over here. Now here also you can see many options in rows as well as in columns, but as I told you this software is very large and it can simulate 1D, 2D, 1D flow, 2D flow, 1D, 2D combined flow. So these are the options which are provided for all the components. So right now what we are going to do, we are going to select a river reach. Okay, we are going to select a river reach option and I am going to draw a reach like, sorry. अरे एक सेकेंड ना. Okay, so right now I don't have some official example for this modeling process, but I have created one example or data set just to make you understand. So what we need to do over here. Now we'll take an example of suppose Vishwamitri River. Now we all know that Vishwamitri River lies in Vadodara, right? And since last 5 to 10 years, every year during normal monsoon also the flooding conditions are occurring over there and resulting into the submersions of nearby areas. So if I want to study that much portion of Vishwamitri River where on the banks of which Vadodara city is lying, then what I need to do, then I need to consider the river reach, means that much section of the river or that much portion of the river where on both the sides the city is situated, right? So I have considered it as a Vishwamitri River section. Now I'll double click on this point. See the point. I'll double click on the point. So a window will be appear. Now this window is asking me to enter the name of a river. So I will enter river Vishwamitri. Okay, and its reach means I'll give it the name 01. So the river name is river Vishwamitri, reach is 01. I click on OK button. So students, here you can see a river Vishwamitri name has been developed with a reach 01. Along with that, you can see one arrow, right, which is moving in the downward direction. So this indicates what? It indicates the direction of flow, which is occurring from upstream to downstream. Means this is the upstream portion of your river, while this is the downstream portion of your Vishwamitri river. And it has been set by default as a it has been set to default by this software that this geometric river reach will show the direction of flow from upstream to downstream in this direction only, and this indicates the positive direction of flow. It means the water will enter from here and moves downstream over here. Are you clear with this? Okay, now let me tell you that there must be a question which is arising in your mind that this river reach is not representing the exact section of the Vishwamitri river, right? We have just drawn it randomly. This is not representing the exact section which we need to carry out modeling of. So what to do in that condition? Like if you want to plot that section of the Vishwamitri river exactly over here, then you need to work with another software known as ArcGIS, where you have to enter the digital elevation model of the Vishwamitri river section of which you are interested to work with. So that is another process which is a very lengthy process. Right now we are not going to do it, and as we are going to model 1D steady flow, it is completely optional, right? It is completely optional to bring that exact location of Vishwamitri section river over here, because we are working in one dimensional flow. And why it is optional, that you will get to know after the end of the modeling process. Okay, I'll tell you at the end that now, due to this reason, it is not required to bring the exact location of the Vishwamitri river over here. It is completely, absolutely fine to draw it randomly with our hands, as we are working in one dimensional flow. If right now we are working in two dimensional flow, then it is not possible to draw a river ridge with hand. Then in that case we need to compulsory plot that original section of Vishwamitri river over here for the modeling process. Okay. Okay, so here you can see that three rivers are connected. River A with a reach name R1. River, this is also River A, but here a junction has been come and it has been divided into two reaches and it has been given a reach 2. Now, if under your study area, which have you taken under consideration, if any another tributary from another river is joining along, then you should also mention it as shown in figure. Okay, if time permits, we can I'll show you at the end that how you can add this tributary or you can add this extra river and you can create a junction. Okay, so right now, because of time limitation, I'm going to I have entered only one reach, which is reach 01 and river Vishwamitri, where water is flowing in this positive downward direction as shown by this arrow, and this represents the upstream of your Vishwamitri river section, while this represents the downstream portion. Okay. Okay, now as you can see on the left hand side, there is a column known as cross section. So we need to plot various cross sections. See, as I told you, that if I want to know the water surface elevation, that is depth of water at various cross sections along my study area, right, then I need to enter the data of that cross sections. Okay, so how it can be what it can be plotted, let's just see. So here I am clicking on this cross section option. Here you can see that a window has been displayed, right? Now this here you can see that there are no values. Here also the plot is not there. So let's just understand this window first. Okay, so the same window is represented over here. Now, as I told you that we need to divide our entire reach into various cross sections. Let me show you just, okay. Now watch this. Don't watch this right now. Don't watch the figure on the right hand side right now. Okay, just watch on the figure which is on the left hand side. So this is the similar figure which I showed you earlier. That is, okay, it is similar to this figure. Right, but what is the difference? You can measure, you can observe this reach as well as this river is divided into number of cross sections. See, See. So this is the cross section number 10. This is the cross section number 9.9. This is 9.8, 9.79. This is 9.7, 9.6, 9.5. Similarly, this is 0.2, 0.1. Okay. So here we are, the topmost section is at upstream side and the lowermost section is at downstream side. See, here it is 0.2, 0.1. Here it is 10, 9.9, 9.8. Okay. So this is the figure which you will get after entering this data. We will also get such kind of cross sections in our considered Vishwamitri river reach once all the cross section data are entered. Okay. So here on the very top you can see the name of the river, that is Fall River, reach that is Upper Reach, and here it is written river station 10. So here you can see this is the river station 10, and the details of this cross section when we entered here, all these details when we enter over here, we will get such kind of cross section of the river station 10, this river station, and this will appear like this cross section. Are you getting? Okay, what we are going to do, we are going to enter the all details of this cross section number 10, and when we will enter all the details, this cross section 10 in 3D perspective plot will be represented as this. Okay, so how we can plot this cross section? This is a line diagram. See, this is, you can also call this at a top view or a line diagram, while this represents the 3D perspective plot. So we are going to plot this cross section or river station number 10 in this table. Okay, so let's enter basic values in our ongoing project. Okay, now here I need to enter the river station first. See, river station is just a numerical value which will represent the cross section. Okay. So before entering all these values, I need to enter that for which cross section of the river I am entering all these values. So for that we need to go to options. Here, see, there is a option called as add a new cross section. So I'll click on this. Enter a new river station. Okay, so this, don't get confused. This river station is only represents a numeric value, that is, it will represent the cross section number on your consider Vishwamitri reach. So because of time limitation, I am going to divide this entire reach only into 4 sections. But as many as sections are there, the accuracy of the results will be high. Okay, let me give you an example that if this my reach of Vishwamitri river which I drawn is of 4 kilometer length, then I will divide this entire 4 kilometer reach of Vishwamitri river into only 4 sections, each of 1 kilometer distance length. That is, at a 1 kilometer distance, I am considering 4 sections. So here I am entering topmost section of a river which is 0, 4. Okay, I'll click on here OK button. Okay. See, here you can see river station is okay. There is no other river than the Vishwamitri river in the list. Only there is Vishwamitri river. So I'll click on the Vishwamitri river. Then here there is only one reach on the Vishwamitri river. So I'll write over. So I'll select the 0, 1. Okay. So now if I'll show you. See, a point has been plot over here. See, this is the upstream side of your river, 0, 4. Means I am going to plot a first cross section at this point. Okay, at the topmost point. Okay, so 0, 4 has been established over here. Now what I am going to do? I am going to enter all the details for this cross section. Right? So let's just study that how and what are the values that we are going to enter. See here now this upper three values we have done with in our example. We have entered the reverse station number 4. Here it is reverse station number 10, which represents this station. And in 3D perspective, after entering all these values, we will get such type of cross section, right? Okay, now here we need to add description about this data. So okay, let's just add that description. Here description is reach 01 of Vishwamitri river, and the cross section is which one? 04. So what I did, I combined this and I gave a description, that is this is the river reach 01 of my Vishwamitri river, and the station, that is the cross section number is 04. Okay, so we are done with this much. Okay, now let's study further. Now here on the left hand side you can see two columns, where in the green background it is written cross section coordinators, right? And here station and elevation, two columns are there. Now on the right hand side of the figure you can see that station is plotted on x-axis, okay, and elevation is plotted on y-axis, and both these plots are in which unit feet. At the downstream where my arrow is, you can see that edit station elevation data in feet. Okay, so the distance of both the x and y axis is in which unit is, it is in feet. Okay, now what this points indicate, so here if you can see that 110, suppose if I take it on x-axis, then for 110 the value of elevation is which? 90. So for somewhat 110 value over here, my elevation is 90. So for 110 I am plotting a point against 90. So I am getting, look at my cursor, this is the point which I am getting after the plot. Okay, so after entering all these values, I will get this cross section. So what is this values? What are these values? So these are the distances of ground points which are taken into consideration during survey carried out, right? So at that point, at a distance of 110 feet on x-axis, the elevation of ground, the ground elevation is of 90 feet. Then at a distance of 120 feet on ground, the elevation of that ground point is how much? 80 point. Then at a distance of 200 feet on the ground, the elevation of that ground point is how much? 78. Right, 278. Then 210, it is 70. Likewise. So this black dots indicates what? It indicates the ground points which are plotted using these two columns. These are the data, students, that you can get from the State Water Department, SWDC, that is the State Water Department from Gandhinagar sector, or you can also get it from the drainage department of your district or city, where you get topographic data in the form of contours, cross sections, etc. Okay, so reading those maps, taking into account those cross sections, you can plot these values. Okay, so this much is done. I hope this is clear. Okay. So let's just first enter this much value in our columns. See, because of time limitation, as I said, we are going to enter only 4 values, as it is a handy operation and I need to enter values, so it will take time. Okay, so these values, as you can see, I have entered the values, but these values are still remaining. So let's just go back to the PPT. Okay, now on the right hand side, again it has been written something which is downstream reach length. So what is this downstream reach length and what is LOB? LOB refers to left of bank, channel and right of bank. So left bank canal, right bank canal and center of the canal. Okay, so how we are going to enter these values? Now, if you can see here, so here these values represents the distance between the two cross sections on the left bank side, main channel, and the right bank side, right bank. Okay, have a look on my cursor. See the distance between these two cross sections, 1 and 2. So this distance, that is LOB, this distance, that is the main channel in center, and that this distance, that is the ROB, that is of the right bank canal. Okay, so this distance we need to enter. So after entering this distance, it can specify the location of the second cross section. And as I told you that once you collect the data, you will get this cross section in the AutoCAD file. So from the AutoCAD file, you can divide the entire reach into number of cross sections as you required. And in AutoCAD file only, you can calculate the distance between the two cross sections. Okay, so that is allowed in AutoCAD, that you can calculate the distance. So with the help of AutoCAD, you can calculate the distance between these two cross sections and you can enter the value over here. So this 225, which is in feet, indicates the value between these two cross sections, LOB. So this 225 is this distance. This is 250, which is the middle distance, and ROB, which is the right hand side distance. Okay, got it? Okay, so let's enter for our example also. Okay, done. Now moving to next row, which is Manning's value. We all know that Manning's rugosity coefficient N plays a very important role, right? Because it depends upon the that material of your channel. So to select, so this is a very critical value, and we need to take very much care in selecting this value, because if this value is not properly selected, we cannot perform. The modeling process will not give you the required, or we can say more accurate results. Now for selecting this values, there is some standards which have been set, and the list of standards you can get from here. See, a question mark is written over here. Okay, so when I click on this question mark, a PDF will get open up. Let's just wait. Okay, see, read here. Selection of an appropriate value of Manning's N is very significant to the accuracy of the computed water surface elevations. Water surface elevations means the depth of water at different cross sections. So some tables are given over here. See, here types of channels and descriptions, and this is the minimum, normal and maximum value. That is, this is for the LOB, this is for the main canal, and this is for the ROB. So if your main channel is clean, straight, there are no deep pools, okay, or if it is clean, winding, some pools are there, so you can select your Manning's constant as required. So these are the floodplains. Then mountains, streams are there. See, here look at option B, lined or built up canals. As I said you earlier that irrigation canals are lined canals. Okay, so for that, if they are made up of concrete and if these are the options, then you can select the corresponding Manning's formula. It means that if your, suppose the study area which you have taken, okay, so if we consider a Vishwamitri river, which is a natural stream. And if it is a straight, it is clean, there are no vegetative cover, there are no roofs full, deep falls, etc., there are no such things are then we can go for these three values of the Manning's coefficient n. Clear? Okay, so coming back to our, so here they have entered these values depending upon their channel, and we will enter values in our, okay, so here I am entering the value. See, this is a data set which has been prepared by me. It as if right now I didn't get any official data set, but this is just for your understanding. Okay, now next we have to plot what? Main channel bank stations. So this indicates the main width of your channel. Okay, it means, see, you can see here that this much is the main width of your channel. Outside this there are the ground points. Okay, so આપણે કહીએ ને કે જે પતલી વિશ્વામિત્રી રિવર તો બહુ પતલી છે, એ તમે જોશો અત્યારે જોશો તો એની કઈ width એટલી બધી નથી. Ground points khasa છે extended, but the main original width of the river is very less. So that width of river is also specified in the data that you will get from the government agencies, right? And that data will also be in the form of cross section, where it has been mentioned that these are the elevations of your main channel width of your stream. Okay, so here they have taken 200. See, these 2 points will be only from the list of points that you have plotted. So here, look at my cursor, point number 3, 200. So at point, at the horizontal distance of 200 feet, the elevation is how much? 78. Okay, and here right bank is up to how much? 240. So at the plot number 6, 240, the elevation is 79. So now in the figure you can see that at 200 the elevation is 78 and it is marked as red one, and the another one at 240, which is the elevation is 79, it is also marked as red one. So these 2 points indicates the actual width of your river. All the other points after these 2 points are just the ground points which are taken under consideration during a survey. Okay, so look at my cursor. So this much portion indicates the actual width of your stream or river, right? So that is also very important to plot. So what they have done, they have plot the distance horizontally at what the main bank stations are lying. So we also plot it. I hope students you are getting this, or if you have any doubt, then we can solve it at last. You just note down your questions. Okay, so as I am entering the same data, I am entering 200 and 240. Done. Now the last column is remaining, which is the column of contraction and expansion. And as you can see here, it has already been, value has already been entered by default as 0.1 and 0.3. So what does this contraction and expansion coefficient means? Now, as we all know that water will undergo contraction and expansion as it moves from one cross section to another in case of natural streams. Right, all the cross sections will not be same. It will depend upon the topography or the back slope of your natural stream. So the water will undergo contraction or expansion, and because of that there will be loss of energy of water, which we need to consider, and this has been set as default for the steady flow analysis, which we can also show, which we can also observe it over here. 1 minute. Okay, you can see here. These are the different values of, 1 second. Okay, let's just have a look on my cursor. In last, it is written that the coefficients of contraction and expansion when the change in the river cross section is small and the flow is subcritical, coefficients of contraction and expansion are typically 0.1 and 0.3. And we all know that most of the natural streams are under subcritical flow, right? Because when supercritical condition will occur, there will be a very high turbulence. So generally the water normally which is flowing in the streams or river is mostly under the subcritical situation. So here the flow under the Vishwamitri river is considered as a subcritical flow with the contraction and expansion coefficients of 0.1 and 0.3. So that has been set as default. Okay, but if we are going to compute for a supercritical flow, then we can change the values. And the values for this and the values for the supercritical flow are also fixed, which has been given in the table, which you can refer later on. Okay, so right now, just moving with this ahead. Okay, so here, as you can see, all the data are completely filled up. Cross-section coordinators are filled up. Distance between two cross-sections are filled up. Manning's value is done. Main width of your channel is done. Okay, so everything is done. Now, I will go to the apply button. Look at my cursor. It is at the top. Above river station, it is an option known as apply button. Apply data. So as soon as I click on the apply data, a plot will be shown here into the box. Okay. Here you can see the plot. It is similar to which it has been shown in the PPT. Except the grids are formed, but that is completely optional. You can keep it or you can remove it. Okay. So here our cross section has been formed. See, this is the cross section. Okay, so these are the station points which are on x-axis. These are the elevation points of ground which are on y-axis. And with the help of all these other values, this plot is done. Okay, so for the first section, the value has been plotted. Now we need to still add the values for the remaining three sections, that is 3, 2, and 1. So I'll quickly follow the same process. So it will result in the saving of our time. I will quickly repeat the same process for the other sections. So I'll again go to the option menu. I'll click on add a new cross section. Again, I enter here cross section number 3. Okay. I'll write the description. From the 4, I can just copy this. Control C, 3, Control V, and instead of 4, I will write over 3. Okay, so I have the data. I'll just quickly enter it. Okay, the Manning's value will remain same, and the left bank will be at 199, right bank will be at 240. Okay, so all data are entered. Yes, it is entered. Apply data. Okay, another cross section has been formed, right? Okay, I add a new option, add a new cross section number 2. Okay, I'll control V. Instead of 4, I will write 2. Okay. So again, I'll enter the values. Okay, so left one I am taking again at 200 and again this is 240. Apply data. Okay, so this is the section number 2. And now I am going to option add a new cross section 0, 1. Okay, let's just quickly finish this. Wait a minute, I have made some mistake. Okay, everything is done. Apply data. Okay, another cross section has been plotted. So here in the list you can see that the different cross sections. See, this is cross section number 4. Again I am taking to cross section number 3. So this is our cross section number 3. This is cross section number 2, and this is cross section number 1. So the 4 cross section has been plotted, and if you can see here in the geometric data window, see, right, this 4 cross sections has been plotted on our river Vishwamitri, because we have divided this entire river into only 4 cross sections, and here you can see these red dots. Okay, so this line diagram also indicates the width of the river through these red dots, right? Now what we need to do, we need to save this data. Our geometric data is done, that is we have solved our second step. So before going for the third step, we need to save our data. So for that we come on minimize this window, come on this geometric data window, when to file, okay, when to save geometry data as, save geometry data as, click flood modeling. See, first of all, see here that the folder is flood modeling only, okay, and the file name is what, steady flow 1D. So this is our file only, right? So we are going to save this geometric data in our file of steady flow 1D. So I will write base geometric data. Okay, base geometric data, I have given the title to this geometry data file, so it will get stored in the file of a steady flow. I will click on this OK button. So, okay, so file has been saved. We can see this in the main window. See, is it visible? In front of geometry, it is written base geometric data, and which is stored in the flood modeling steady flow dot G01, which is the extension for the geometric data, first data. If we want to enter the another data, then the extension will be dot G02. Okay, so here once, as I said that here once the name is come, it means that your geometric data is saved. Now let me just show you the okay. See this plot. This is the 3D perspective plot. But here there is no water, right? So what we did? We plotted this from this. We plotted this from this, but here the final figure is shown. But here you can see the plot. This is the actual width of the river. Dear students, this might be not plotted perfectly because the data set that I have prepared is on my own. But believe me, when you plot the data originally, it will be a very beautiful view. You will be amazed by its view. Okay, so this is just for your understanding. Like we went to, okay, let me close the other windows. Okay, so from this data, we went to this data. Okay, so we defined a river reach of Vishwamitri river, and we divided the entire river into only 4 sections because of time limitation. You can divide it in number of cross sections so that you can get more what we can say accurate results. Okay, so this is the first this is the cross section number 4. So this is this cross section is represented over here. This is 3, this is 2, and this is 1. Okay, clear? I hope this much is clear. So